Good day, everybody. Today I want to look at Jacobi elliptic functions. So I'll go to this Wolfram Math World website for the standard definition. Of course, you can find them all over the place on the web. But basically, if you just want a quick definition, we have this value u, which is given by an integral, and u will depend on, we like to use phi, so u will depend on phi and k, and it'll be this integral from 0 to phi, 1 over square root of 1 minus k squared, sine squared of t dt. And of course, this t can be any dummy variable. Sometimes you'll see a theta there, among other variables, but I like t. So u is in terms of this integral, which we can't in general evaluate for most values of k. We can when k equals 1. We'll get to that later. Or k equals 0. So u depends on phi, as I'll emphasize more graphically in a bit. Also, phi then depends on u. There is a one-to-one relationship. So if each value of phi gives a value of u, conversely, each value of u will give a value of phi. So we can think of phi depending on u. It's called the Jacobi amplitude. So phi is some function of u and k. And then sun u, which also depends on k, but snu is going to be the sine of that amplitude, Jacobi amplitude, which is sine of phi. And similarly, kun u, cnu will be cosine of phi, and dun u, dnu will be this quantity. It's also can be thought of as d phi du, which is 1 over du d phi. That'll give this same value right here. So again, I rewrote this definition for u in terms of phi, so we have that. And then in most of the graphs we will later see, but I put it right here, that there's a quarter period that we call capital K, nice and confusing, but that'll be the integral from 0 to pi over 2 of this same integrand. And so most of the graphs I look at, I have little k 0.8, which leads to the quarter period, capital K, being just about 2. So again, we can graph u in terms of phi. That would be easy to do as a standard function. You just graph this integral. But I kind of wrote it parametrically for what's going to follow. So another way to do it is we want the horizontal axis to be phi, and then the vertical axis is u of phi, which is this integral. So that's how you can graph u in terms of phi, just from the definition. That one's super easy. But if I want to graph phi in terms of u, then parametrically all I have to do is switch the x and y there. So now I'll have the horizontal axis be u, and then the vertical axis be phi. So that's now gives me the graph of the Jacobi amplitude, or phi in terms of u. So there's the graph. So as we saw, Cn of u is defined by kun u is cosine of phi of u. So to graph that, then I'll graph y will be cosine of phi, and that's the vertical axis, and the horizontal axis will be u of phi. I need the horizontal axis to be u if I want to graph Cn of u. Right? So for y equals Cn of u, to graph that, the horizontal axis has to be u, so that's what we'll do parametrically. The vertical axis is then cosine of phi. Similarly, if I want to graph sun u, which is sine of phi, just have the horizontal axis be u, and then y will be sine of phi. And of course, to graph dun u, just have the horizontal axis be u, then y will be this quantity, square root of 1 minus k squared sine squared phi. So there's the graph. Just for emphasis, I'll do it on the graphing calculator. So notice the parameter of phi can be any variable, really. except on the graphing calculator, it's forced to be, the parameter is capital T. So I rewrote it this way. So we'll graph it using capital T as our parameter for graphing. And then the integral, the dummy variable of integration can be anything as long as it's not the same upper limit. So I wrote it as V for Kunyu or W for Sunyu. So this is the same thing right here, but just instead of phi for the upper limit and sine of phi, I have capital T. And then for the variable of integration, it could be anything that's not capital T. So of course I can graph U in terms of phi on the graphing calculator, but I won't do that. And I can graph phi in terms of U. In other words, I can graph the Jacobi amplitude, but I won't do that either. And of course we can graph Kunyu and Sunyu is the one I'll graph. So here we are. Look at what I've typed in already. So I've got the integral 0 to capital T is what I have to use. There's my integrand. Here I use U as the dummy variable. I didn't want to put that on the paper because then we use U for the U in terms of phi for defining Kunyu and so forth. So I thought that wouldn't look good, but I don't know, for whatever reason I use U as the dummy variable of integration here. So that's that. So let's look at the graph then. So simple as that. To graph y equals Sunyu, I just need the horizontal axis U in terms of phi, and then y sine of phi, or capital T. So graph. It starts pretty quickly at first, but does slow down quite a bit as it moves along and calculates. So here I have the graph over 5 quarter periods, or 5 quarter periods. So, and each tick marks 2, which is roughly what the quarter period is. So look here. So there's 2, 4, 6, 8, and that's 1 full period. And then here's 10, which would be 5 quarter periods. So there you have it. So a little deeper look at the graphs. First, here's my integrand over a quarter period when k is 0.8. And so if you integrate, you get the u in terms of phi, right? So there's the integrand, and u is defined as that integral. You can see it right there. So u is the integral from 0 to phi, 1 over square root of 1 minus k squared, where k is 0.8 right now, sine squared t dt. And we can kind of see, so if I integrate from 0 to pi over 2, I'll get the same area under the curve if I then go from pi over 2 to pi. But anyway, so this is u in terms of phi from 0 to pi. And just to beat it to death, I'll go 0 to 2 pi. So here's a look at it. So there's the integrand. Of course, it's pi periodic, but the area under the curve from 0 to pi over 2 is the same as the area under the curve from pi over 2 to pi. And then after that, of course, it just repeats anyway. So again, as stated, if we get u in terms of phi, then I can get phi in terms of u. Like here I did it numerically. Pick a value for u, and in here it solves numerically for the value of phi to get that value of u. So again, just a basic idea. Since u in terms of phi is 1 to 1, it's invertible. Now just to look at what happens for different values of k. So the previous was all at k equals 0.8. If k equals 0, then the integrand is actually 1. And so then u equals phi. And that's what I see graphed right here, u equals phi. As k approaches 1, what we're going to approach is the arc cosine of 1 over cos u, which is secant, hyperbolic secant of u. And I have that graphed as well. So on the vertical axis, I've got phi. On the horizontal axis, I have u. We didn't label them, but u is on the horizontal here. Phi is on the vertical. So as k increases, not too much change. So we'll see that happens a lot. Things don't really start happening until around 0.8. But so here we are. There's my 0.8. But if I keep going, you can see it is approaching that hyperbolic. Well, it's the arc cosine of 1 over cos u. If that was too quick, I do have a slower version. So again, there's the definition of u, but I'm graphing the inverse, which is easy enough to do just parametrically. X is u, y is phi. So here I start at 0.99, just to go a little slower. Get the idea. We'll see it on paper at some point. And then as stated, to get y equals CNU graphed, just parametrically. So x is u of phi, y equals cosine phi, graphs CNU. So here's a look at CNU. It's actually, it's distorted, but this is the graph of cosine, the regular cosine curve. You could say u is the horizontal axis, so this is just cosine u when k is 0. But as k increases, it's kind of a slide, and then one thing I noticed, we start getting changes of concavity, which might be interesting. But we approach the hyperbolic secant of u. That's in blue. 1 over cos u. That's what we approach. Here it is for k equals 0.99. Yep. Happened pretty quick there. If we want to think about the points of concavity, here it is for k equals 0.96. So I've labeled them, and you can kind of tell. You've got changes of concavity at those points. So right now we're concave up. We also switch at the axis, so we're concave up. Now we switch to concave down, and we stay concave down until we get to that other inflection point. So I stay concave down. Now I switch back to concave up. Concave up. Now switch to concave down. And so stay concave down till you hit the u axis, and switch back up. So how interesting is that? The points of concavity start appearing when k equals root 2 over 2, the square root of 1/2. So if I type in this decimal approximation of square root of 2 over 2, square root of 1/2, it is rounded up. That 812 was rounded up. So if you had more decimals, it would be 811. I forget what comes after that 1, but something bigger than 5. So it rounds to 2. So I'm slightly above root 2 over 2. And so these points of inflection occur here at this x and y. So y is roughly 0. It's really, really close to the axis. So the points of the new points of concavity start at the axis, and then they come outwards. They come outwards pretty quickly. So let me just go to say 0.7072. So maybe not too quickly, but so that's where the points of concavity occur. 0.71. Start to separate out 0.81. And they've gone most of the way they're going to go. They don't keep going away. They have a limit. This point heads towards the limit of the point of inflection of y equals hyperbolic secant u, which I guess might make sense. Also, if I do a point below root 2 over 2, or a value of k, below root 2 over 2, then I'm not getting any points on the graph. You're not getting, if you solve, it's a complex number. So we'll see what happens. So unable to plot those points, they were all complex values. Anyway, so here's the graph of soon u, horizontal axis u, vertical axis sine phi. So u of phi, sine of phi. If you want to look at the graph for different values of k, when k is 0, it's actually just regular sine u. But then as k gets bigger, oops, gets distorted. And if we're interested, it's going to approach hyperbolic tangent of u. And here's dnu, dnu for k equals 0. dnu is 1. That's easy to see from the definition. When k is 0, it's easy to see we get cosine, sine, and then 1. But for other values of k, it looks like this. Oops. And it heads towards hyperbolic secant of u, just like CNU did. All right, so that was a look at the graphs. Back to some of the things I mentioned. If I re-look at the definition, so since u depends on phi and it's 1 to 1, we can think of it as also phi depends on u, the amplitude of u. And then kun u is cosine phi, cosine of the amplitude u. Soon u, sine of phi, dun u. d phi du, which is 1 over du d phi, will give me this by the fundamental theorem of calculus. And then now, so some properties. Yeah, I haven't done the properties yet. So kun squared plus soon squared, well, that's just cosine squared phi plus sine squared phi. And dun squared is 1 minus sine squared, 1 minus k squared, soon squared. So that should be easy to see. In fact, I have that right here as well. So same thing I just said, but now typed up. So again, properties, kun squared plus soon squared is cosine squared plus sine squared, so that has to be 1. Dun squared is square root of 1 minus, or dun is 1 minus, square root of 1 minus k squared, sine squared. So dun squared is 1 minus k squared, sine squared. All right, so I just said look at the derivatives this way first. So you can take d du of soon u will be d du of sine of phi of u, but the derivative of sine is cosine, and then the derivative of the argument is the definition of dun u. So the derivative of soon u is kun u dun u, because cosine phi is kun u. So that's easy, and the others are easy too. Derivative of kun u would be derivative of cosine phi, but the derivative of cosine phi is negative sine phi, and then times the derivative of the argument is dun u. So we get that. And depending on how you want to define dun u, you can define it as this square root or get it from the property, but either way. Then the derivative of dun u, if you take the derivative of this, it's to the 1/2 power, multiply by 1/2. The whole thing's to the negative 1/2, so it's in the denominator. Then times the derivative of what's inside will give you a 2, which will cancel the 2, but I've got a minus k squared, sine phi, cosine phi, derivative of phi. But the derivative of phi is dun u, which is this denominator anyway, so then they cancel and you're just left with that. So there's the derivatives. For concavity, I thought of another way to express the derivatives. Did soon first. That's right. So if we want to graph y equals soon u, then I'll graph y equals phi, x equals u of phi. Right, so we did that. And then the derivative of soon u du is just dy du, which is the same as dy dx, because x is u. This is u of phi. So just do dy d phi over dx d phi by the chain rule. And then since y is sine phi, I'll get cosine phi, and dx d phi right here. So if you take the phi derivative of this by the fundamental theorem of calculus, it'll be just 1 over this square root. Plug the phi in for t. So it'll be that. And flip this up, and that's the definition of dun u. So You can get the derivatives this way as well. If I want the derivative of kun u, I mean, it's pretty much the same idea, but I want to get the points of inflection, so I kind of wanted to think of it, how I graph it. So if I graph y equals kun u, which is cosine phi, so this is how I'd graph it, and x would be u. Then the derivative is dy du, which is dy d phi over dx d phi, since x is u. And that'll be negative sine phi, dx d phi, easy to see. Flip it up, and you get that. And here I got dun u through the properties. But this allows me to get the second derivative. So the second derivative will be d squared y dx squared. And that'll be d dx of dy dx, which is d dy dx d phi over dx d phi. And so I have to take the derivative. Well, there it is. There's what we got before. And then dx d phi is that. So we'll go through too much there. But, use the product rule here. Get this. And if I flip this up, then I'll get a square here. And this will cancel. So flip this up and multiply through. And then simplify by factoring negative cosine phi out. Now I have two negatives here, so I still have one left over. And negative cosine phi here. So this is what I have. So I get this. So this is the second derivative. And then if I put it equal to 0, we get cosine phi equals 0. And that occurs at phi equals these values, which corresponds to these values of the quarter period, which is where it crosses the u-axis. Right, so that's a point of changing concavity. But we also get this could be 0, except if k is too small, you don't get a solution. Like if k is 1/2, I end up getting sine squared is 2. It's not until you reach 1, where once k is big enough so that this is less than or equal to 1, and that occurs at root 2 over 2. So we can find the values of phi in terms of k once k is in between these values, and so I can get my points of concavity. Lastly, so I put k equals 1 here. Notice if k equals 0, it's easy as well, and things are the circular trig functions. But when k is 1, I just get cosine squared here, so which means I get secant, and then the integral of secant we can do. We get this, and so I can simplify. Let's do it quickly here. But because I knew the answer, I kind of knew the direction to go. But so if u is this, then negative u, I just take the reciprocal, and notice if you add the two together, it gets this. And then if you get your common denominator, things simplify to this. So e to the u plus e to the negative u is this, but then if you factor out a 2, it ends up just being this. So then divide by 2, and that just becomes cos u is 1 over cosine phi. So cosine phi is 1 over cos u. This is when k equals 1. So that would be hyperbolic secant of u. So that's the kun of u when k is 1. And then from back to this equation, well, I guess take the reciprocal. Cos squared is 1 over cosine squared, or secant squared, and then cos squared is also 1 plus sinh squared. It's the identity of hyperbolic functions. So I can solve for hyperbolic sine, subtract 1, and this is then tangent phi, which means sine squared, which is tangent squared divided by secant squared, is hyperbolic sine squared divided by hyperbolic cosine squared, cosh, or tangent squared. And things are positive, so you can take the square roots, just keep the positive values. One other thing to note, so I mean, why does it happen? I mean, if you go to the quarter period will approach infinity as k goes to 1. Quite see it here, but if pi over 2, there's a vertical asymptote and go to infinity as phi goes to pi over 2 when k equals 1. But as long as you're below pi over 2, you can get values. All right. So next, we're going to look at a way an ellipse can give us all the values of kunyu, sunyu, and dunyu. And so got a particle going around an ellipse right now. And let's look a little more right here. So we're going to start with the major axis along the y-axis, vertical, and the minor axis, horizontal, along the x-axis. So we'll have x squared over a squared plus y squared over b squared equals 1, with b bigger than a. If b equals a, you get a circle and you get the regular trig functions. A useful special case is if a equals 1, and sometimes I'll use that, but I kind of want things in full generality. So we can have any ellipse, and our k is the eccentricity of the ellipse, which will be the square root of the major axis squared minus the minor axis squared over the major axis, so for us, square root of b squared minus a squared over b. So if we know a and b, we can get k. And conversely, if we have a k, then we can get the ratio of b to a, or a to b. But b to a will be 1 over the square root of 1 minus k squared. So the eccentricity determines k, or conversely, k determines the eccentricity of the ellipse. So here's two ellipses with the same eccentricity, one with minor axis 1, major axis 5/3, the other with minor axis 1.5, major axis 2.5. So same eccentricity. And so they would work the same. The value of k is the same for both of these. And we can see in the picture how we're going to define sunyu and kunyu. We're going to go straight from the point towards the origin, but where we intersect the unit circle, the x and y value will be kunyu and sunyu respectively. Note, I'm using phi here so we can have it similar to the standard definition of the Jacobi elliptic functions, but phi is essentially the same as the usual polar angle theta, and we can go round and round. So if I look at the major 3 Jacobi elliptic functions, there's 9 others, maybe I'll mention at some point, but the major 3 and the other 9 are just ratios of these 3. Our kunyu, which as we saw was just x over r, so if you go straight towards the unit circle, that will be the value. So x is the point on the ellipse, x over r takes me to right here, and y over r. So if you just divide by r, you're now on the unit circle. So that's kunyu, sunyu, and then dunyu is a over r, the minor axis divided by r. And of course, as I mentioned, the convenient special case, just fix the minor axis to be 1. So dunyu would be 1 over r, but regardless, the most dunyu can be is 1, because that's the least r can be is the minor axis. R can be the minor axis or larger. So dunyu is 1 or smaller. We also define du, and I define u more precisely, but for some work, all you kind of need is that the differential du is going to be r over a d theta. And as I wrote here, when you fix a to be 1, it looks like du is r d theta. And that kind of looks like a length. It would be like a length on a circle or something, but it's misleading. You divide it out by the minor axis, so it really should be a dimensionless quantity. And so really what du is it's just a stretching of theta, as we'll see, and it stretches the bigger r is. I guess I'll continue with the property. So defining So we kind of started over. So defining kun-u and sun-u as x over r and y over r, x and y points on the ellipse, r is the distance, the origin is to that point x, y, then r squared is x squared plus y squared. So we easily get this identity. And from the equation of the ellipse, we can solve for x in terms of y is the way to go in this case. Maybe I'll show what happens if you solve for y in terms of x. It doesn't work out as well, but I'll only do the correct way right now. So we'll solve for x in terms of y. So just subtract this, multiply by a squared, and really I just need x squared, so I won't take square roots. So x squared is a squared if I distribute a squared over b squared. And if we substitute that into the formula for r squared, x squared plus y squared, then I get this for x squared. And then I could essentially add 1 minus a squared over b squared times y squared. But that was for k squared, the eccentricity up here, right? So k is this. So k squared is 1 minus a squared over b squared. So I have r squared is a squared plus k squared y squared. And now if I just divide through by r squared, then I'll get 1 on the left. I'll get a squared over r squared plus k squared y squared over r squared. But dnu is a over r, and sun-u is y over r. As a reminder, there they are. So we get the same two major properties that we had before. And now for derivatives, I could actually do it through the graphing way. Maybe I'll show that, but if we want to do it a different way through the ellipse, then we'll start with the fact that for any point on the ellipse, right, so if I have a point on the ellipse, x will just be r cosine phi. I mean, that's standard polar equation stuff. So x is r cosine phi, takes me to x from the origin. And similarly, y will be r sine of phi, because phi is essentially the polar angle. So if I'm defining kun-u as x over r, and I want the derivative kun-u du, then I'll need the derivative of x over r. So I'll take the differential of both sides here. Differential of cosine theta is negative sine theta d theta, and the differential of x over r I'll just leave as is, because that'll end up being kun-u. Now sine theta is y over r, so I'll sub that in. And I want du, now remember I defined du as r over a d theta. So to get an r over a, well, I just put an r over a there, but I don't want to change the problem, so I also multiplied by the reciprocal, so this is the same as that. And now this quantity is du, and then I have these two. So I've got this quantity times du is this derivative of x over r. So just divide by the du. And since cnu is x over r, dx over r du being negative y over r, a over r, means d du of kun-u is negative y over r, a over r. But y over r was sun-u, a over r was dun-u. So we get the derivatives. The others are done the same way. Take the differential here, multiply by a over r and r over a, so that I have r over a d theta, which will be du. And then this, I have differential dy over r. And just quickly, we get dy over r. Once this becomes du, you divide, is these two things. So d du of sun-u, x over r times a over r, which is kun-u, dun-u, based on how we defined the Jacobi elliptic functions from the ellipse. And then there isn't a convenient trig function for a over r, so you can go to a boxed property, well, namely this one, dun squared, and take the differential. Well, actually just take the derivative with respect to u of both sides of this identity, that property, and you pretty easily get the derivative of dun is negative k squared sun kun. So once you have the two properties and the derivative of any of the three Jacobi elliptic functions, you get the other two. And so that's where you get the other two from the other property. So That kind of characterizes the Jacobi elliptic functions. The two properties and then these derivatives, the values. Maybe quickly, it's almost a repeat of the above, of the standard definition. But so another way to get the derivatives, so skip all this. This is just defining here, although you do have to be a little more precise for u. So du is r over a d theta. We could kind of get away with to get the derivative properties more precisely. This other way to get the derivatives, I need u more defined like so. And of course, this will result in du d theta is r over a. Again, properties come quickly. We'll do that. But if we wanted to graph kun u or sun u or dun u, just like I did before on the graphing calculator, well, I can graph, well, I want to graph x over r. But x is r cosine phi. It's r cosine theta, but phi and theta are the same here. So r cosine phi divided by r depends on phi, but in the end it'll cancel. So that'll just be cosine phi. And similarly, sun u is y over r, but y is r sine theta. So divided by r will give me sine theta or sine phi. And then if I want to plot, I have to plot x is u and y is cosine phi. So I would get the derivatives the exact same way as before. If you're graphing y equals sun u, graph y equals sine phi, x equals u, and then find dy dx. And you get this, which of course cosine phi is cn u dnu. So again, here we can see as I go around the ellipse, I'm going around at a constant rate. So going around the circle at a constant rate. But theta and phi are always the same value. You can compute r. This is for the major axis 2.5. So that's as big as we can get. Oops. And the minor axis is 1.5. So 1.5 divided by 2.5 is 0.6. Sun u is 1 here. Kun u is 0. Continue on. So we're getting periodic functions, but they're not the same as the periodic functions of sine and cosine. Again, as a special case, if the minor axis is 1, then all you need is the major axis bigger than 1 to get the ellipse with major axis vertical. Here it is 2.5. So before, I drew the ellipse bigger than the unit circle. The ellipse could be inside the unit circle or partially inside, whatever. But it is convenient to have the minor axis 1. Just don't lose information. So here's a look at same idea. But here as I said, the major axis is 2.5. What I'm going to look at now is interpreting u. So again, for any ellipse, we can solve for r in terms of theta. I almost had it before, but if I redo the work, solve for x in terms of y, sub it in, and we got to this equation before. But now I'll sub in what y is. So before I just divided through by r squared to get that dun squared property. But if I replace y with r sine theta, move it to the left-hand side, divide in square root, we get r in terms of theta, also in terms of the minor axis and the eccentricity. So r of theta of the ellipse with eccentricity k and minor axis a. And we want du to be r over a d theta. That's what will work. So I need u to be the integral, and we'll put the lower limit 0 is the way to go. Upper limit theta. So here is r over a. So u of phi is this integrand, which is the same integrand for the standard definition. And anything can be the dummy variable. So it could be t, or it could be theta, which is r of theta. But we don't want to get too mixed up in that. So I do kind of switch back and forth between theta and phi, just because I like theta for the polar angle. So I kind of like that. But I also like phi to be the parameter to match it with the standard definition. But phi and theta are the same thing. So u is this integral. And so people have tried to interpret this integral. When it's r d theta, they're trying to interpret it as a length. But if it's r over a, you see it's not an interpretation of a length. It'll end up being kind of a stretching. I first thought of it as an average value. So for example, if you compute, if you define the average value, it's the integral divided by the length of the interval. So if I want the average value for any value of phi, it would be this. So I'll look at some graphs shortly, but here's one here. So if you've got your integrand, the average value, r over a, and it's measured in units. So it's r measured in units of the minor axis. Then of course, since I've defined, right, so here's r, so r over a is just this. So if that's the average, it's a running average. As theta increases, it kind of levels off somewhat. But r over a, that running average times theta, would just be this times theta. The thetas will cancel, and we get our standard definition of u. So that's the way I like to think of u. That's the best way I could think of it as u. It's the average of r in units of the minor axis times theta, or phi. Maybe I should have used phi here. And then of course if you take du, it's r over a d theta still. Maybe to look at it more clearly here, there's a graph of r over a for when k is 0.8. There's the integrand, r over a. Or in other words, this is kind of r in units of the minor axis a. And then the running average as phi increases is given by this curve right here. I don't know if this is a good analogy, but if you think the distance a particle has moved, if it has velocity v, you can find by doing this integral. But another way to think of it is, well, if you computed the average velocity, then the distance a particle travels is the time it's traveled times its average velocity during that travel. Yeah, what a brilliant analogy. Again, so if u is the this integral, which is the same as the total phi times the average of r divided by a for that phi, then du will be r over a d phi. And so infinitesimally, u is a stretching of phi or theta by an amount r over a. And then for larger intervals, same thing happens. So if you take any two angles, u at phi 2 minus u at phi 1 is just the integral from 0 to phi 2 minus the integral from 0 to phi 1, which gives me this integral from phi 1 to phi 2, which again I'll think of as the change in phi times the average of r over a over that interval, because then these would just cancel again. So essentially, the change in u for any two phis is the average of r over a for those values of phi times the change in phi. And r over a is always going to be bigger than 1. So as I said, any interval length in u is just a multiple of the length of phi. So here's a look at going around the ellipse. Eccentricity 0.8, major axis 5/3, minor axis 1, of course vertical. And we get our kunyu, sunyu, dunyu based on where we are on the ellipse. It's easy to compute. Phi, r, and x, and y. So all these are easy to compute. U, the only way to compute that is to have that more precise definition or version of u. Du is r over a, d theta isn't quite precise enough, so you need that integral a little more precisely. But the important thing to notice is that for any phi, we have an r. R changes from a low of 1 to a high of 5/3. Again, I want r in units of its minor axis, which in this case is 1. So again, here's a plot of r in its average, its running average. But here I've done it in not r over a, but r in terms of a, its minor axis. So to have a dimensionless quantity, you do r divided by a, and so you're computing r in units of its minor axis. So it's always got a minimum of 1 when your theta's at 0, pi, 2 pi, etc. So as you cross the x-axis, that's when r is 1. But otherwise, r is bigger than 1. And this is the exact same thing, except before I had it as theta, and now I just changed it to phi, because phi and theta are identical. So those were all with k equal to 0.8. If I change k, you don't see too much difference until k gets up there. Then here's a running average graphed along with r. Right, so eccentricity of say 0.91, r gets to be like 2.5 times its minor axis. That was like for this picture. So as I said, there's a stretching going on. And I'll first look at a stretching of uniform amount. So right now I haven't stretched it, and I'm going to graph and stretch sine phi. So here's sine phi, not stretched. So there I am at 2 pi, 6.3 almost. Now, if you want to stretch vertically, you multiply the y value by a constant. If you want to stretch horizontally, you divide, right? So if I want to stretch it horizontally by a factor of 2, I would graph y equals sine of phi divided by 2. But I'm not doing that. I'm graphing it parametrically. So parametrically, actually what I do is I still graph y equals sine phi, but x will be phi if I just graph y equals sine phi. But if I want to stretch it, then I can multiply the x component by 2. So this is the x component of my parametric equation. Right now r is 0, so there's no stretch. Or the stretch is, I multiplied by 1, and y is sine phi. But anyway, so as r increases, I stretch. But this is a uniform stretch. So I'm stretching uniformly. So you get that idea. And that's what the Jacobi elliptic functions are. They stretch, but not uniformly. They stretch based on the value of r in that ellipse. So once again, here's the running average. This time I've got it typed for us too. So it's always bigger than 1. It's 1 at the beginning. Say it's undefined there. I put it as 1. But you know, it increases until you reach, well, until it intersects itself, and then it starts decreasing a little more, then increasing again. It somewhat levels off for the most part, but I won't go to large values of theta. So there's the running average of r divided by a. And this is for k equals 0.8. Let's look at for other k's. Here's b over a. I wrote b over a, probably, but a is 1. So I'm going to fix a to be 1. And so right now b is 1 times a. So in other words, I have a circle. So r divided by a is 1 for every value of theta or phi. But as I increase K, you don't see too much difference there, but stretching it. So the unit circles graph, but then I'm graphing the ellipse. So the B value is really B over A. Is see if I go to 0.8 here, right there. So now it's 5/3, or about 1.67. So R over A has bigger values right here. And notice those are at pi over 2 and 3 pi over 2, the multiples of odd pi over 2, odd multiples of pi over 2. And there's like there'll be no stretching right here when we're at multiples of pi. So I only went up to K equals 0.96, but so it's a pretty stretched ellipse. So R over A looks like that. So I'm going to go back to K equals 0.8 and look at the R over A. And I'm going to find the running average. There's actually 80 subdivisions I made here, 20 in each quadrant. So 80 subdivisions, 20 in each quadrant. And I'm going to find the average R in each of those 80 regions. And so it looks like that. So obviously you've got a maximum R over A average in that tiny little delta phi or delta theta. It's almost 1.67. It's not centered at pi over 2. That's only an endpoint. But so you can get closer to 1.667, 5/3. But so that would be where it's a maximum. But the minimum is always bigger than 1 for any positive subinterval. It's pretty close to 1, just about 1. So what the graphs of the Jacobi elliptic functions are, they're a stretching of sine and cosine, but not uniformly. So let's look at how much u is stretched by. It's stretched by r over a. du is r over a d theta. Delta u is r over a delta theta. So there's different stretching depending on the theta. So let's look at the stretching of u for different values of k. It's hard to see much happening for the small values of k, but then it starts to happen quickly, and yeah. And again, there's the most stretching at phi equals pi over 2. That's where u is stretched the most. And again, I only went to 0.96. So u is stretched, almost no stretching at 0 and pi. So this is how u gets stretched. I graphed it both along so you can see with the phi, but then also just vertically so you can see the stretching that way. Again, if I look at b over a for the ellipse, and this always goes to pi over 2, that's where the maximum stretching will be, right here at the green. So at 0.96, b is it's actually 25 over 7. So a nice little Pythagorean triple there. So to see how this stretching changes the graph, and we'll get Sun-u and Kun-u. Well, I'll start with Sun-u. So Sun-u, if k is 0, Sun-u is just sine. And the maximum stretch is this value here, b over a. So there's no stretch at all. Everything's stretched by 1. So if we want to see the stretching even better, we can look this way. So we can see the stretching. So we've got a maximum stretch where the phi equals pi over 2 and 3 pi over 2 occurred. Not much stretch where phi equals 0 or pi. In fact, if I do it quickly, if we keep an eye on the points near u equals 0, they don't seem to move much at all, but because they're not stretched much. So it's pretty easy to see where the most stretching occurs. This is with 0.96. If I go to 0.8, Again, not a little less stretching, but so then the maximum stretch is at 1.667-ish. So if you look at the values there, so I'm seeing U now on the horizontal axis. So these points are stretched and these are not too much. And again, the stretch amount for each of those intervals, because there's 80 of them, there's also, so I looked at everything in terms of the 80 subintervals of 0 to 2 pi. So the max stretch is just about 5/3, and the min stretch is just over, a little teeny bit more than 1, when k is 0.8, which this graph's for. This is now the horizontal axis, so how much u gets stretched. Again, that's all based on this. So the average r is 1 here, and its maximum here. The most stretching for any k is going to be at phi or theta equal pi over 2, 3 pi over 2, and almost no stretching at phi equals 0, pi, multiples of pi. And odd multiples of pi over 2 has the most stretching. So similar idea with cosine. If k is 0, this is the graph of cosine, and now we're going to stretch it, but not uniformly. We stretch it more at phi equals pi over 2 and 3 pi over 2, but this is where cosine is 0, so it'll be different than the sine being stretched. Sine got stretched at its max and min of 1 and -1. Cosine gets stretched at its zeros, the maximum stretch. So stretch, 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 and so maximum stretch at the zeros. Hopefully you can see that. If I do it quickly, you see almost no stretch on the left. And then, of course, there's like no stretch here at the other peak. So no stretch there, maximum stretch here. And we can see the stretch amount is going to be by B over A. All right, so that was a long video, but hopefully you gained some understanding of the Jacobi elliptic functions and their graphs. So I guess I'll finally wrap it up here for at least this video. I do want to get into, there's another popular way to define the Jacobi elliptic functions with a horizontal ellipse. So I'll look into that and compare the two. They have different integrands, so I'll have to resolve that problem. And then we'll also look at differential equations that the Jacobi elliptic functions solve, and in particular solving the pendulum differential equation. Might do that a couple different ways. So, all right, yeah, I guess enough for this. So, thanks if you were able to make it through, and hopefully you found it worthwhile. Also, I put a lot of documents in the description. Hopefully they will be beneficial to you as well. Thanks again, and have a good day.